Hello everyone. My talk will be about geometry of helicoidal modeling. What we first need to do, we have to define spaces over which we assume our material and surrounding space. Then we develop theory of dual numbers, dual functions, and matrices we use in this framework. This will serve as a foundation for the third and fourth sections. And in the end, I will tell about some possible applications in mechanics of this type of modeling. We consider our material as a smooth embedding of manifold B into a three-dimensional space S. The dimension of B depends on the situation. So if you have a beam theory, you would consider dimension 1, for shell theory, dimension 2, and for general case, dimension 3. We write Xi for local coordinates of the material body and Xi for coordinates of the surrounding space in absolute frame of reference. Our concern is with three-dimensional bodies where each particle has 3 translational and 3 rotational degrees of freedom. And the usual approach here is to consider 2 of those quantities as independent, but by transforming from the 6-dimensional space into the triples of dual numbers, you can put it together to a single quantity, which is called rototranslation. I will talk about. What are actually the dual numbers? They are numbers in this form where epsilon to the power of 2 equals 0, and we will denote such numbers with the head symbol. Dual numbers don't form a field because it is not possible to find inverse for pure dual numbers in multiplication operation. So it's just a 2-dimensional field over the real numbers. This is how such a dual function looks like, where phi 0 and phi 1 are the real functions of 2 variables. And it can be proven that such a function is differentiable if and only if those 2 conditions hold. And if so, we would call them synectic functions. So the dual matrices, we will consider dual matrices in which the entries will be dual functions. And such matrices have interesting properties like infinitely many eigenvalues, which is not the case for the real or complex matrices. So this is how such a matrix can look like. Let me here just briefly mention some names in the history of dual numbers. They were invented by W.K. Clifford in 1873. The importance in mechanics was later recognized by Kotelnikov and Study, and Dimenberg made a significant work with essential monograph about the screw theory. So we will write phi for general rotation, which depends on 3 parameters, which usually are angles of rotation around x, y, and z axis. And there will be 2 important functions, the axial and the cross function. The first one assigns to screw matrix, screw symmetry matrix, its axial vector. And if such matrix is not screw symmetric, it will take the screw symmetric part. The other function works in the other direction. So to one vector, it assigns a screw symmetric matrix. So let us consider now basic rotation around x-axis, translation along x-axis by length of A. And we can put those 2 transformation into such a dual matrix, where, as you can see, the real part is simply rotation matrix, and the dual part is multiplication of the cross function applied to the translation vector and the rotation matrix. This construction is of course general, so you can consider arbitrary rotation, arbitrary translation vector, and construct so-called rototranslation field. And what is important here to mention that its entries are synectic functions, which mean that you can differentiate such a fields and construct some tangent vectors. We also computed how dual numbers, how eigenvalues or eigenvectors for such a transformation look like. So this is the case for just a simple rotation around x-axis and translation along x-axis. And for the general case of the translation vector, it ended up in this way. And what we are currently trying to figure out is what is geometrical meaning of such a eigenvector. So as I said, each particle has 6 degrees of freedom. Orientation is given by rotational matrix alpha. Position is given by the position vector x, and they can be put together to form this dual frame, which we call oriented position. So it's given by this dual matrix. So if you want to just from this frame get the orientation, you can just look at the real part. If you want to take the position, you can multiply this by the inverse to alpha and then apply axial function to the dual part. And how actually the rototranslation applied to this works. So if you take general oriented position, general rototranslation applied together by matrix multiplication, this is the resulting oriented position you get. So the previous orientation is just rotated by this matrix phi, and the position was first rotated around the origin and then moved along vector t. So if you would consider this as this matrix multiplication as an action of group, you could find out that these elementary rotations and these elementary translations form together a Lie group. So this is how actual action of some action of rototranslation particle looks like. So you can see how the orientation and position changes. And of course, if you have a Lie group, you can construct by differentiating Lie algebra, which is spanned by those 6 dual matrices. In the next step, we construct the curvature tensor to better understand how particles move and orient themselves within the material body. And so it's defined by this way. For each, this curvature tensor consists of 3 curvature vectors kj, where j refers to one of 3 material coordinates, and a with index j refers to just the derivative of oriented position with respect to this material coordinate. The curvature can be expressed in this way and then separated to the real and dual part. When as you can see, the real part depends only on the orientation change, while the linear part depends on both position change and the orientation change, which wouldn't happen if you would just consider rotation and translation separately as independent. There is one property which can help with simplifying those equations. For example, if you would have particle with constant orientation in the material, the angular part will be always 0. and the linear part will have this interesting form. There is one proposition for a given curvature vector. This equation holds where the Tj is some symmetric matrix of coefficients from this vector. And this brought up a question how actually what is this? What this is it's a first order system of partial differential equations. So for example, for two-dimensional case, it looks like this. So there is hidden the curvature vector. And what we found out to solve this system is that the solution for functions v and w, it lies on the circle with given radius, and this function phi is given by two of those integrals, which have to be equal together. And for a three-dimensional case, the situation is similar. The solution lies on a sphere with given radius c, and the functions phi and psi are given by those integrals. So what you get in the end are 6 equations that has to hold together with some boundary conditions. So how can be this applied in practice? You can, for example, consider fiber composed, fiber reinforced composites, where each fiber translates and rotates with respect to the matrix, which can affect the general behavior of the material. What you can also do is it can help design drills and milling cutters to where the rotations can help you to optimize the curvature and cutting angles of such tools. And in the end, for example, you can, by this modeling, model the structure of bone tissue, including the fibers and pores. And what you can do with it is to investigate the response of this bone tissue to some different type of loads, or study the fracture mechanics, how it works. So yes, that's everything for me. Thank you for your attention.